All right, let's pick up with this next problem. What's the probability that our friend arrives more than 10 minutes late? Well, again, we can draw our uniform distribution. And remember, it's 1 over 30 tall. The horizontal axis runs from 0 to 30. So more than 10 minutes late. Here's 10 minutes. And we need more than. So that means this rectangle to the right of 10 that I just shaded. So the length of that rectangle is 30 minus 10, which is 20. And remember, the width is 1 over 30. So the probability that our friend arrives more than 10 minutes late, so x is greater than or equal to 10, is length times width, which is 20 times 1 over 30, which is 20 over 30. And you can just put this in your calculator, or 0.6667. Okay. Here's another one of the reverse way. So it's 1 p.m. There's a 45% probability your friend will arrive within how many minutes? Well, again, drawing our distribution. And so 45%, that's a little bit less than half. So 0.45. And we need to find the length of this shaded rectangle. So remember, the probability is length times width. We don't know the length, but we do know the width and we do know the probability. So 0.45 equals the length times 1 over 30. And remember, when you divide both sides by 1 over 30, and when you use your calculator, do not forget to put it in parentheses so that you don't mess up the order of operations in the calculator. So here, our length is 13.5 minutes. So there's a 45% probability our friend will arrive within 13.5 minutes. Okay, you should do this problem on your own. Pause the video, and it's just like the previous problem mostly, but with different numbers. So you try it on your own and then start the video again and see if you did it right. So the random variable x represents the time we spend waiting in line at the checkout at the grocery store. Suppose the time is uniformly distributed with all intervals of times between 0 and 10 minutes being equally likely. Draw the uniform distribution. So it's uniform, so again, we have our rectangle. And it says we're going from 0 to 10 minutes this time. And so remember, our probability goes on the vertical axis, our random variable x goes on the horizontal axis, and the rectangle is 1 over whatever values at, well, the distance from 0 to 10. So in this case, it's 10. I should say, if instead of starting at 0, we started at 5, then the probability would be 1 over 5. So we should, the height of the rectangle, I mean. So we should make a note that the height of the rectangle is 1 over the length of the rectangle. And the length is the length of the horizontal axis. Okay, verify that the area is equal to 1. So area is length times width, which in this case is 10 times 1 over 10, which is indeed 1, so we're good. What's the probability we wait in line between 2 and 8 minutes? Okay, draw our picture. So we have 10 minutes, 0, 1 over 10. Put a line for 2 minutes, put a line for 8 minutes, and we want in between. So let's shade that rectangle. So the length is 8 minus 2, which is 6. So the probability that we wait between 2 and 8 minutes is the length times the width, which is 6, times 1 over 10, which is 6 over 10, or 0.6. Okay, what's the probability we wait less than 4 minutes? So less than 4 minutes. Draw our distribution again. So here's 4 minutes. Less than means to the left side. So the length is 4 minus 0, which is 4. And the probability that we wait less than 4 minutes is length times width, which is 4 times 1/10, which is 4 over 10, or 0.4. Okay, there's a 33% probability that we'll wait for how many minutes? So again, draw our rectangle. Wow, that was a little bit wonky sided. It's okay. So we have something we don't know, but we do know that the area in here is 33%. So 0.33. So remember, the probability equals the length times the width. So in this case, 0.33 equals the length times 1 over 10. Divide both sides by 1 over 10. Being careful to put that fraction, the 1 over 10, in parentheses in your calculator. And we get 3.3 minutes is how late our friend will be. Well, sometime within 3.3 minutes. That concludes our discussion of uniform probabilities. So in the next video, we'll pick up with the normal curve, which is a second type of continuous probability distribution.